Hi everybody and welcome back. This is section 1.2, and in section 1.2 we're going to take a look at some types of data. This is going to be a pretty quick one, pretty short section. Key concept here is talking about the data that we collect. How do we label it, or how do we talk about the data that we collect, and how we can use some sample data to talk about populations. All right, so more terminology. We have these two words right here, parameter and statistic. Okay, a parameter is a numerical measurement, so a number that is used to describe a characteristic of an entire population. Right? So it is a numerical measurement to describe an entire population. Now, the characteristic you're describing just depends on the scenario. It could be anything. But if you were attempting to describe an average person in an entire population and you want to talk about their height, then a parameter would be a number that would describe the average height of a element, a person in that population. Or if we go back to my favorite example, our cans of Coca-Cola that are supposed to have this in them, but chances are they're not gonna, because we don't live in a perfect world where we can put exactly 12 ounces in every can of Coke. Then if we were going to describe the average amount of soda in every single can ever produced by that machine or on that day, or however we define our population, then that number we would call a parameter. Now, contrast that with a statistic. A statistic is also a numerical measurement. It also describes a characteristic, but it describes the characteristic of some sample. So what that would mean was, if I went down to production floor and I grabbed 30 cans and I measured how much soda was in those 30 cans, and I averaged out the amount of soda that was in those 30 cans, whatever that average would be a statistic, because it will be a number of ounces in the can that described a sample that was taken from a population. Now, big picture, in the world of statistics, what we want to be able to do is we want to be able to use these statistics to make predictions about these parameters. Most of the time, it is going to be impossible to know a parameter, because there's no way to measure the entire population most of the time. Outside of some very rare instances, it's almost impossible to measure a population. There's just too many. Okay? So we measure samples, right, from a population, and our hope is that we can use that sample statistic to approximate or to discuss a population parameter. All right, let's take a look at some examples and see if we can differentiate between the things. So in these examples down here, our job is simply to decide whether the number that is being given, the numerical measurement, is describing a population parameter or a sample statistic. All right, we'll start with question number 1 here. Right? A survey of several hundred collegiate student athletes in the United States found that during the season of their sport, the average time spent on athletics by students was 50 hours per week. Right? So there's our measurement, and it is describing how much time student athletes spent studying. Right? Oh, I'm sorry, not studying. They spent on their sports, because, they're athletes. All right, so the average time they spent on their sport. So that 50 hours is describing this. The question is this 50 a sample statistic or a population parameter? Right? So we have to look at where it came from. Well, it came from a survey of several hundred collegiate student athletes. Now, that several hundred, is that all of the student athletes that there are? because if it is, if several hundred is all of them, then that 50 is a parameter. If that several hundred is just some of them, then that several hundred is a sample, and that 50 would be a statistic. Now, I'm not sure how many collegiate student athletes there are in the United States, but I'm certain it's more than just several hundred. There's probably several hundred on some football teams. So I'm betting with a high degree of certainty that we're looking at a statistic here. Okay? Because it is a number that is describing a sample from a population. All right, let's move on to number 2 here. Number 2 reads, the freshman class at a university has an average SAT score of 514. So there's our number. That number is describing the average SAT score. And who is it describing it for? Well, it's describing the SAT score for the freshman class. I'm hearing, I'm reading, I'm interpreting this to be everybody in the freshman class. And if it's everybody in the freshman class, then that 514 is describing an average SAT score for an entire population. So then our 514 here would be a parameter because it is a number describing the average SAT score for everybody in the freshman class. And that everybody part of it is what makes it a population. All right. Moving on, number 3. In a random check of several hundred retail stores, the Food and Drug Administration found that 34% of the stores were not storing fish at the proper temperature. Beyond the fact that that's ew, there's our number, our value, our numerical measurement that is describing something. It's describing a proportion or a percent of the stores that were not storing fish at the proper temperature. Okay? Now the question is, how did they arrive at that number? Did they get that number from talking to every store out there? Or did they get that number from talking to some of the stores? Well, it was a random check of several hundred stores. Is that all the stores or is that some of the stores? I'm hearing that that's some of the stores, not all of the stores. So that's a sample. So that means that we're looking at a statistic here, because that is not all of them. That is a sample. We gathered our data from a sample. So our data, when we crunch the numbers, that numerical measurement is a statistic. I'm having a hard time saying statistic right now. Right? Okay, let's take a look at number 4. Number 4 reads, I know, the average salary for 45 of a consulting firm's 300 engineers is 72 grand. Okay, I've got 3 numbers in this one. This is the first one where we got a whole bunch of numbers, and I got to try to figure this out. Okay, which of these is the number that is attempting to describe something? Well, I'm reading that the average salary is 72 grand. So the number that's attempting to describe something is that 72 grand. And what is it attempting to describe? Well, it's attempting to describe that average salary. Okay? Where do we get that number? Well, we got that number by talking to 45 out of 300. Well, that 300, since that's all of the engineers, that would be the population. The 45 that we talked to, that would be the sample. And the 72 grand, since it came from the sample, we would say that that is a statistic. Right? If we had talked to all 300 engineers, all of the engineers, then it would be a parameter. But since we got it from just some of them, from a portion of our population, we got it from a sample, it is a statistic. Right? Looks like we got two more, so let's see if we can get through these. Problem number 5 reads, a survey of 1,058 College Board members found that 56.3% think that college completion is a major priority or the most important priority of their board. Right? All right. The 56.3% is attempting to describe something. It's describing the portion of the people who believe that college completion is a major priority. So it's describing that aspect of the board members' beliefs, right? Okay. Now, here's my question. Where did the number come from? Well, they got it from a survey of 1,058 College Board members. Okay. Is 1,058 all of the College Board members? Because if it is, and we talk to everybody, we're looking at a parameter. If 1,058 is some of the College Board members, then we're looking at a statistic. Now, I'm going to be honest with you. I have no clue how many College Board members there are. So I don't know whether 1,058 is some of them or all of them. And since I can't tell, the safest thing to say is call it a statistic unless you know it's a parameter, right? Since I don't know how many College Board members there are, I can't tell whether 1,058 is all of them or not. And if I don't know for certain that something is a parameter, I assume it is a statistic. So it is a statistic until you can show me that it isn't. Right? All right, last one. 62 of the 97 passengers aboard the Hindenburg airship survived its explosion. All right, so 62 of the 97 survived. So there's our data. This is our data. Oh, how do you spell data? I don't think it has an extra T on the end. There's our data. And what is it? Oh, wait. Is 97 all of the passengers? I believe it is. And 62 of them survived. So these numbers, these numerical measurements are describing everybody. So we're looking at parameters. We could use that to find the percent that survived, which would be a parameter. We could use that to find the percent that did not survive. That would also be a parameter. So we're looking at parameters there because we have data about everybody. Okay, some more terminology. All right. On the highest level, data falls into two categories: quantitative and qualitative. Quantitative data is our numerical data. It consists of numbers representing counts or measurements. It can be two different types of counts or measurements. It can be discrete or it can be continuous. Discrete data is countable data. It's the one or the two, but nothing in between. So if we were counting, if we were gathering data on the number of televisions that you have in your house, well, you could have one TV or you could have two TVs, but you can't have 1.5 TVs. So it would be quantitative data because it's counting things, but it would be discrete quantitative data because it has to be that whole number, those countable counting numbers. Continuous data is, we call it mathematically uncountable, but what it means is it could be one or two and everything in between. So let's change it and say, what if we were gathering data on how many hours of television someone watched? Although I don't think we call it that anymore. I think we refer to it as screen time rather than television because, we're evolving as a society. So if we were going to measure how much screen time, someone could have 1 hour, someone could have 2 hours, but someone could also say an hour and a half. So you get everything in between. So you could have continuous quantitative data. Right? The other type of data is qualitative. Qualitative data is names or labels. So when you think of qualitative data, think color, shapes, that kind of stuff. And we call that categorical data. Okay? So what's your favorite color? What's your eye color? What's your hair color? Things like that. Right? And then there's categorical data. Right? Well, categorical data is data that is numbers, but numbers don't mean numbers. Numbers don't mean a count. Like if someone were asking you for your social security number, that's a number technically, but it is a number that you use to count things. Okay? Your phone number is a number, but it's a categorical data number. Any sort of ID number, like my employee number for the college, it's a number, but it doesn't mean anything. Right? A good way to think about it, if you're worried about numbers being categorical or numbers being quantitative, think this. Can I add two of them together and divide by 2? And would that mean anything? So if one house had 2 TVs and another house had 4 TVs, could I say there's an average of 3 TVs? And that would make sense because I could add the 2 together and divide by 2 and get 3. If one person's employee number is 2 and another person's employee number is 4, and I add them together, do I get an employee number of 6? That doesn't make any sense. So that would mean that those aren't numbers in the quantitative sense. They're numbers in the qualitative sense. They're a label. Right? All right, we got 6 questions here where we're going to see if we can determine what type of data these are. The weight of dogs at an animal rescue. Well, those are going to be numbers. 4 pounds, 5 pounds, 6 pounds. Could you have 4.5 pounds? Sure, you can have a 4.5 pound dog. And if you had a 4.5 pound dog, that means you're looking at quantitative data. Specifically, you're looking at continuous quantitative data. So this would be continuous. Q-U-A-N-T-I-T-A-T-I, quantitative. I always struggle with that one. There's too many T's in the end there. Continuous quantitative data. Right. How about the carrying capacity of long bed trucks? Like I could have a truck that can haul 2 tons. You could have a truck that can haul 3 tons. I got 2s and 3s and maybe a 5-ton truck or a 10-ton truck. Right? So those are numbers. If I take a 5-ton truck and a 10-ton truck and add them here, I get 15 tons. That makes sense. So that means we must be looking at not qualitative categorical stuff. We must be looking at quantitative again. So these are quantitative. Are they continuous or discrete? Could someone be 1.5 tons? Sure could. So that means we're looking at, again, continuous. Right? Number 3, hair color, several students. Well, what would that data look like? Well, it might be like black, brown, red, whatever color they have. Well, those are definitely not numbers. So they're definitely not quantitative. They must be qualitative. And so they must be data labels, colors. So we're looking at qualitative data here. Qualitative data. Student ID numbers. Well, that's exactly the example that I was talking about, except for I didn't say student ID. I said my employee ID, which we said was a qualitative data set. Okay. How about weights of infants at their 6-month check-in? Well, weights of infants at their 6-month check-in. Could you have a 4-pound baby? Could you have a 5-pound baby? Could you have a 4.5-pound baby? Could we add them all up and get an average baby? Looks like we're looking at another continuous quantitative data set. Okay. Last one, species of animals in a forested region. Species of animals in a So we'd be looking at things like what? Deer, raccoon, maybe javelina. I don't know. Those live in forested regions? I guess they kind of do. All right, javelina. Javelina. I think I got that right. Yeah. Words. That's going to be just like number 3, right? It's just a bunch of words. I can't add them together. I can't do anything with them. So we're looking at qualitative data. Okay. All right. So the idea of this section, and that's it for section, well, we got levels of measurement, but that's it for this section about types of data. And the idea here is that not so much that you're going to use these words directly, but if you were to see this word or to see that word, if you were to see someone say, oh, this is quantitative data, or this is qualitative data, would you understand what they're saying? All right, last thing we have to take a look at, just this page, that, and then we'll be done, is the idea of levels of measurement. Okay? And this is a way to further classify data in a slightly different way. The levels of measurement of data, they give you an idea of what you're allowed to do with statistically, what number crunching kind of math you can do with the data. And there are 4 levels of measurement, from the lowest to highest: nominal, ordinal, interval, and ratio. The nominal level of measurement is the lowest level of measurement, meaning it is data that is the least crunchable. It is the data that we can do almost nothing with. Okay? This is definitely going to be qualitative data, so it's the names and labels and categories only. We can't really order it in sense of this is better than that. Okay? So if you were gathering data about hair colors and you decided that your data was black, brown, and red, there's your data set. How do I order that? Is brown better than black? Is black better than red? Is red better than brown? How does it work? So I can't necessarily order it as low to high. Now, I could tell you the counts for each of these, like I saw 40 people with black hair and 20 people with brown hair, and in that sense I could say there were more people with black hair than brown hair, but I can't say that black is better, ranks higher than brown. I can just say that it was more frequent than brown. Right. One level up from nominal is something called ordinal, the ordinal level of data. Now, in the root of ordinal is order. So this is data that can be arranged in order somehow, but the differences between data values either can't be determined or are meaningless. Right? And so let's say someone asks you to order your 3 favorite types of food. And so I would say, for me, number 1 is Indian. I love some good Indian food. Number 2 is Thai. And number 3 is probably Italian. Okay. I ordered them, so I can put them in some sort of an order, but the differences between the data values are kind of meaningless. Like, do I like Indian twice as much as I like Thai? Or do I just barely like Indian more than Thai? The fact that it's 1 and 2 doesn't really tell me something. Right? Think about people running a race. Someone's going to come in first place, and someone's going to come in second place. And the difference between first place and second place could be a second, could be a minute, could be an hour. All that first and second means is someone came in first and then someone came in behind them next. But it doesn't tell you how far apart first and second are. Right? After that, the next level is to hop up to the interval level of measurement. Now, interval looks a lot like ordinal in that the data can be arranged in order, but the differences between values can be found and are now meaningful. Right? So what does that mean? Well, what I can do is I can subtract values and that difference now means something. Right? So let's say that the first person to finish the exam finished at 10:15. The second person to finish the exam finished at 10:20. I can now tell you that the second person took 5 minutes longer, because the difference between those two is meaningful. Right? The difference is there's no natural 0 point. And since there's no natural 0 point, it makes it harder. Right? All right. Another way to look at it, if that one doesn't work for you, is temperature. Right? So let's look at that. Suppose on one day, random day you pick, the temperature in Phoenix was 100 degrees. And let's say on another random day, the temperature that you picked was 50 degrees. Can we say that on the 100-degree day, it was 50 degrees warmer than on the 50-degree day? Yeah, we can do that because 100 minus 50 is 50. Can we say that the 100-degree day was twice as hot? Well, no. I don't know that 100 degrees is twice as hot as 50 degrees. I know that the number 100 is twice the number 50. But is that how temperature works? Is 100 degrees twice as hot? Right? And the reason that temperature does not work like that is because of what this is. What does 0 mean? Like, if it was 0 degrees, what does that mean? Does that mean there's no temperature? Or is that just some measurement on a scale? Now, if we're talking about Fahrenheit, 0 really means nothing. It's the goofiest scale ever, because in Fahrenheit, water freezes at 32, it boils at 212, and 0 is just some measurement that's 32 degrees below freezing. So I don't know. A natural 0 is when 0 actually means you have nothing. Right? All right, so think about it this way. If 0 means you have nothing, then you're not interval level of measurement. So would 0 degrees mean you have no temperature? And if 0 degrees means you have no temperature, then yeah, it doesn't work like that. Time doesn't work like that. The year doesn't work like that. What was year 0? Does that mean we didn't have time back then? It's weird, but it's a hard one to wrap your brain around. But the biggest thing is to look for 0. Right? Ratio level of measurement. Now this is the highest level of measurement. This is data that can be ordered, differences mattered, and there is a natural 0. That means 0 means nothing. So if I asked you, and I collected data on this, how much money was in your pocket right now in cash, right? And someone told me that they had $14, and someone else told me that they had $28. Could I say that this person, undo that. Where's undo? I don't know where undo is. I don't see an undo. That's interesting. All right. Could I say that the $28 person has $14 more than the $14 person? Yeah, because I can do subtraction. So differences make sense. Could I say that the $28 person has twice as much money as the $14 person? Yeah, because 28 is twice 14. That's where ratios come into play, and that's why this is called ratio level of measurement. Because in this data set, if I told you that I had $0 in my pocket, does that 0 mean I don't have anything? And yeah, if I told you I had $0 in my pocket, that would mean I have none of the quantity that is being presented. In this case, I have no money. All right, let's see if we can come up with some ideas of whether or not these things are levels of measurement, what level of measurement they are. Right? All right, so we'll start first one. Data was collected, okay, about the movie genres playing at the campus theater, and they said that they have an action, an adventure, a comedy, drama, and a horror. Okay, so I've got data. There's my data. My data is those words right there. I can't do, I mean, currently it looks like they're in alphabetical order, but other than that, I can't order them. Is action better than adventure? Is adventure better than drama? Is drama better than I can't order them. So that data is categorical data. It's qualitative data, and I can't order it. So that's going to be the lowest level of measurement, or nominal data. You could even go further and say this is nominal qualitative data. Okay. Number 2, the top 5 occupations in the United States with the most projected job growth for the year 2026 are: number 1, personal care; number 2, registered nurses; number 3, home health aides; number 4, food prep service workers; and number 5, retail salespersons. Okay, they're ordered, the top 5. Between those two, how much better is 1 than 2? Can I subtract and figure it out? Can I make a ratio and figure it out? Or personal care is just more than nursing? I don't know. I can't tell how much more. I can't make a subtraction and make sense out of that. I can't make a ratio. So this is data that I can order, qualitative data that I can order. So it's ordinal level of measurement. So this would be ordinal qualitative data. The New York Yankees, moving on to number 3 here, the New York Yankees have won a record 27 World Series championships, with their victories occurring in those years right there. Okay. So there's my data. My data is all of these numbers right here, and these are years. Looks like I could put them in order, so it's at least ordinal. Can I subtract 2 of these and say, oh, look, between here and here, there was a 15-year gap? Can I subtract? And if I can subtract, that's good. Could I divide? Would there be a year 0? And would 0 make sense? I don't think there was a year 0. So I can put them in order, I can subtract, but there's no year interval. So this would be quantitative and interval level, or interval quantitative data. Okay. Number 4 down here, last one, looks like the American League home run totals by team. We got the Yankees that had 274. We got this. I got a whole bunch of data for the American League. Okay. So I got data. Can I subtract? Can I say that these guys and these guys, that the Los Angeles Angels had 28 more than the Tigers? Yeah, I just subtracted and it makes sense to say that. Okay. I know that isn't here, but let's say that there was a team down here, I don't know, the Big Boys or something. I don't know team names. And let's say that they had 113 home runs. Right? Let's just pretend there was. And I'm doing this to make the math easy. Could I look at these guys and then look at those Angels? And could I say that the Angels had twice as many home runs as the Big Boys did? Is 226 twice 113? And I just made a ratio, and that ratio makes sense that the Angels had twice as many. And since that ratio made sense, that means that we are looking at a ratio level of measurement data set. All right. So again, 1.2 was all about terms and words and concepts. And the idea is that if someone were to throw these at you in a problem or talk about them, would you be able to go, okay, I know what that means. I know what that means. And that's what you should take away from section 1.2. The last little bit down here is about some other terms we might run into. If we run into the term big data, what are we referring to? We're referring to data sets that are so big and so complex that you're going to need massive computers running in parallel to make sense of it. Right? If you see the term data science, what is that? Well, it's a relatively new field of study, but it's the application of statistics along with computer science, along with software engineering, where we're taking the concepts from here, programming them, and writing software to make them work. Right? There's lots of areas where data science is being used. It shows up a lot in finance as ways to look at the big picture of big data and how to make money off of big data. Okay? We also have issues with missing data. What does missing data mean? Well, it's when you have data that is missing completely at random, or if the likelihood is independent of its value or any other values in the data set. So missing data is when we have data that's missing from a data set for reasons that don't essentially matter. They don't affect the outcome. Right? If it's not missing at random, we worry. And then we got to worry about correcting somehow for missing data. Right? Oftentimes what we'll do is we'll just delete people out. So if someone only fills out half a survey and we're missing half of their data, delete them. Delete it all. Right? Other times we will impute missing data values. And what we mean by that is we'll take a look at the rest of the data in the data set, and we'll, using stats and using some some prediction software type stuff, we will put in data values for that missing data. Right? This used to be how everything was done. If you didn't have it, delete them. If you didn't have it, delete them. Now they've found ways to do this. And what I mean by do this is do this well. Do this in a way that it doesn't negatively impact anything. Right? All right, that brings us to the end of section 1.3. Lots of terminology. Again, you notice that we have not done math yet. We have not added, subtracted, multiplied, divide. We're just talking about and getting those ideas and those words defined. Right? All right, have a great day.